So let's discuss 555 timer and then the multivibrator that we can build with 555 timer. So 555 timer is an 8-pin IC, very commonly used ICs in the timing circuit. And some of the applications are given right over here. Use it in one shots, delay timers, pulse generator, bunch of applications that you can read, logic clocks and frequency division circuits and stuff like that. And why it is called 555 timer? Because as you will see in the circuit, you have three 5 kilo ohm resistors basically connected in series with a reference voltage, and that's why it's called 555. So let's look at the circuit. So this is the basically internal block diagram of 555 timer. This is the IC, 8-pin IC of 555 timer. So you have VCC. Basically it operates with a single voltage source, VCC. Pin number 8, which is right here, power supply. Pin number 1 is grounded, is ground. Pin number 2, so you have two comparators, comparator 2 or upper comparator. In your book they're calling it upper comparator, they're calling it lower comparator. So you have the upper comparator, you have the lower comparator, and pin number 2 is connected to the inverting terminal of the lower comparator, and pin number 3 is the output pin. Pin number 4 is the reset pin. If you send an active, I believe it's an active low signal on the reset pin. So if you send an active low signal, active low means if you send a low signal, it will activate. Then it is going to reset the output of your 555 timer, irrespective of what is the condition at the input. So pin number 4 is the reset pin, and pin number 5 is the control, which is connected to the inverting terminal of the upper comparator, and it is also connected at the junction of these two 5 kilo ohm resistor, if I call them R1, R2 and R3, although all three values are same, so all of them are R's, but I'm just naming them R1, R2, R3. So they are it's also connected at the junction of R1 and R2, and this pin plays a very important role in the determination of how these two comparators are going to operate. Pin number 6 is the threshold, which is the pin connected to the non-inverting input of the upper comparator. Pin number 7 is called the discharge, which is an output pin, which will become either grounded or open circuit based on the condition of the output. And as we discussed, pin number 8, of course, is the VCC. So how does this circuit operate? So the output, again, output is going to oscillate between a high level and a low level. Low level is usually grounded, actually it's pretty much always grounded, and the high level is whatever high level is, VH. Of course, the high level cannot exceed the VCC voltage. It will saturate when it gets close to the VCC voltage. So let's say V high is approximately equal to VCC, whatever voltage you're using. For VCC, there's a range of the voltage for, it's a very flexible IC. So I think there is I forgot what is the range of the VCC that you can use for 555 timer, but it's a pretty good range that you can use. Okay, so if you do not use control input, right, what's gonna happen? This VCC is going to control basically the voltage that will appear at the non-inverting input, at the inverting input of the upper comparator, as well as the non-inverting input of the lower comparator, if you don't apply any signal over here. If you do apply a signal over here, of course that signal is going to appear here, and then that signal is going to control rest of the voltages over here. In general, control basically is grounded through a capacitor. And in all the text, including your book, they say use a 0.01 microfarad capacitor. I'm not really sure why they're using that, but in any case, so this is basically deactivated by grounding it through a capacitor. Now, why they're grounding it through the capacitor? Because of course capacitor blocks any DC voltage. So basically it's going to block that ground. So that's ground is not going to appear over here. Otherwise this pin is going to be ground, right? So or any DC quantity, that DC signal that is coming from the ground, DC current or anything, capacitor is just going to block everything from there. But why a specific value? I'm not really sure about that, but they use in general in every book they're using a 0.01 microfarad capacitor, and then they ground that and connect it to control. Alright, so this is generally how you're going to operate this. There will be no signal coming from the control pin. That means the voltage is going to be divided through the network of these three 5 kilo ohm resistor, hence the name 555, remember. So what will be the voltage at this point? The voltage at the inverting terminal of the upper comparator is going to be the voltage across these two 5 kilo ohm resistor. That's going to be, using voltage division, 2/3 of VCC, right? So R2 plus R3, which is 10K. So you will have over here, let me just do math over here. So you have 10K divided by total resistance, which is 15K, times the total voltage, which is VCC. So that's going to be 2/3 of VCC. That voltage will appear over here. And then the voltage that will appear here is the voltage across this R3, which is again 5 kilo ohm. So that's going to be 1/3 of VCC. So the voltage appear here is 1/3 of VCC. These two voltage quantities are extremely important because based on these two voltage conditions, the output is going to change between the high level and low level, as you will see pretty soon. Okay, so I got this from a website, and it's a good description. There is also good description in your book as well, but this is pretty good description as how things are working. So go over that, but in general I explained what is going to happen. Basically, as I said, the main two voltages that you have to be careful is this voltage, which will be 1/3 of VCC, and this voltage, which will be 2/3 of VCC. So if the threshold, so let's look at this figure instead of reading that. Let me explain you. Observe, if the threshold is greater than 2/3 of VCC of the upper comparator, then the VD is going to be greater than 0. So the output of comparator 1 will be 1. And if the voltage at the trigger is less than 1/3 of VCC, then again this VD is going to be greater than 1, and the output is greater than 0, and the output will be greater than saturation VSAT. So the output will be VSAT over here if threshold is greater than VCC, and output will be VSAT over here if your trigger voltage is less than 1/3 of VCC. Now if they are not, then of course the output is going to be negative VSAT for this. So control flip-flop, that is basically going to decide what voltage is coming from what level is coming from the comparator, and based on that it will provide a voltage to Q1 and Q2, and the output is also going to go to the power amplifier, and then it's going to go to the output. So we're going to look at the condition as how they are going to work. Okay, so you can read this. I explained you a little bit, but the important thing is this table. So there are 4 conditions. In general, 2 conditions will happen, as you will see when we design the circuit, but there are 4 conditions. If trigger, that is pin number 2, well, remember what is pin number 2? Pin number 2 is your lower comparator inverting input. And as we discussed, if it is less than 1/3 of VCC, below 1/3 of VCC, then the output of the lower comparator will be 1, otherwise, or high VSAT, otherwise the output will be negative VSAT or 0, whatever. Threshold is the non-inverting input of your upper comparator, right? Non-inverting or inverting? Let me check. I think it's inverting. I may be wrong. No, non-inverting. Okay, so 2/3 of it's a non-inverting input of upper comparator. So if threshold voltage is greater than 2/3 of VCC, the output of the upper comparator is going to be high. Now, irrespective if their output is high or low, in this table, the output state, the output condition, pin number 3 state is defined. So it is defined that if trigger, pin number 2 is below VCC3, that is, if the output of the lower comparator is VSET or high, and if pin number 6 is less than 2/3 of VCC, that is, the output of the upper comparator is at negative VSET or low. So one comparator, lower comparator is high and the upper comparator is low. Then the output of the IC is going to be high. Okay, so this is the condition we have to meet to make the output of the IC to be high. Condition number D, if pin number 2 is above VCC by 3, that is, the output of the lower comparator is going to be negative VSET, and if pin number 6 is greater than 2 VCC by 3, that is, the output of the upper comparator will be VSET. So again, one will be negative VSET or low, the other will be positive VSET. One will be low, the other one will be high, if for the output condition to change basically. So the output is going to go to low. So the upper comparator output high, lower comparator output low. Then the output of the IC is going to be low. And based on the status of pin number 3, the discharge pin, pin number 7, if the output is high, it becomes open circuit, right? So no current will go in there. And if the output is low, it becomes grounded. It becomes grounded. Now, what happens if you have other than these conditions? Then condition B or C. If pin number 2 below VCC by 3, right? That is, if your output of the lower comparator is high and pin number 6 is above 2 VCC by 3. If the output of the upper comparator is high as well, VSET. If both of them are VSET, then it just remembers whatever the last state was, either low or high. And likewise, discharge pin remembers whatever the last state was. And likewise, condition C is if pin number 2 is above VCC by 3, the output of the lower comparator will be low, negative VSET or 0. And pin number 6 is below 2 VCC by 3, then the output of the upper comparator will also be low or negative VSET. Then once again, it will remember the last state, right? So as you will see in our circuit, basically these two conditions will be employed, condition A and condition D. And the output will be either high or either low. When condition A will be satisfied, both these conditions has to be satisfied. When condition D is satisfied, both these conditions have to be satisfied, right? So let's move on and then see how we can create a stable multivibrator. And remember, we're going to be using this table to create this. All right, so this is the circuit. Observe both trigger, pin number 2, and threshold. So pin number 2 trigger is the negative the inverting input of the lower comparator, and pin number 6 threshold is the non-inverting input of the upper comparator. Both of them have been tied together. So whatever condition is going to happen at these two inputs, that condition will be same, right? That condition will be same. Remember, we need those two pins to have either below VCC by 3 or below 2 VCC by 3, or above VCC by 3 or above 2 VCC by 3 for the output to go high or low, right? So they have been tied together, and there's a capacitor connected to the ground, and pin number 2 and 6, that means the voltage at these two pins is the voltage across capacitor, right? This voltage, which is VCT. Okay, pin number 5, pin number 1 is grounded, of course, and pin number 5, which is control, as I said, it is connected to ground through a 0.01 microfarad capacitor. So control is not playing any active role. Your pin number 8 VCC is connected to two resistors in series, RA and RB, and pin number 7, which is discharge, is connected at the junction of RA and RB. Now remember, pin number 7 can either be open or ground based on what is the condition at the output. If output is high, pin number 7 is open. If output is low, pin number 7 is grounded. As again, we will look at this table 7.1. So how does this circuit operate? Let's look at the circuit to how it is operating. So once again, the output will be either high or low. As I explained, it is low is going to be 0 and high is going to be V high, which either can be close to VCC or less than VCC. It cannot exceed VCC, of course, because VCC is the highest voltage in the circuit. And the capacitor voltage is going to be charging and discharging. So charging and discharging like this, charging towards high and then discharging towards low, something like that. And the waveform is you will see this pretty soon. Okay, so right here. Okay, so here. So output voltage is high and 0. When it is high, we call this time to be TH, time corresponding to when the output is high, and when it is low, we call it TL, time corresponding to when output is low. Now observe that TH and TL are different. Why they are different, as you will see, because the time constant of the RC circuit is different when the output is high and low. Alright, as far as capacitor voltage is concerned, remember I told you that two voltages are important, of course, VCC by 3 and 2 VCC by 3. So this capacitor voltage, actually it will oscillate. Once it will settle down, when it will go to steady state, then it will oscillate between VCC by 3 and 2 VCC by 3. So VCC by 3 when it goes from VCC by 3 to 2 VCC by 3 when the output is high, and then it starts discharging from 2 VCC by 3 to VCC by 3 when output is low. So let's look at how the circuit is going to behave. So let's say at time reference time t is equal to 0, so this is our 0 reference time right here. The output goes to high and the capacitor voltage was at VCC by 3 and it start charging towards VCC, and during that course it will go to 2 VCC by 3. Alright. So at time t is equal to 0, output goes to highest state. When output goes to highest state, pin number 7 goes to open circuit. So this pin is going to become open circuit at that time when output goes to highest state. When it will become open circuit, then what do you have? You have VCC connected to RA. Of course, no current is going to go here since it's open. All the current is going to flow through RB, and then all the current is going to go to the capacitor. So this circuit is going to appear as a series circuit: VCC, RA, RB, and capacitor when the output is high. Okay, and this circuit is right here: VCC, RA, RB, and capacitor, and the initial value of capacitor, initial voltage on capacitor is VCC by 3. Okay, so what's going to happen? We know again, like we did the derivation of series RLC circuit, series RC circuit, first order. We know that the capacitor voltage is comprised of the steady state value, natural response. Now, steady state value, of course, if in this circuit you let the capacitor charge, then it will hit VCC, of course, after it is fully charged. Of course, it's not going to go to VCC, it's going to start discharging again. But if you let it charge, then the final charge that can appear across the capacitor when the time tends to infinity is VCC. So that's the steady state value of your capacitor voltage. And then A e to the power negative t over tau h. Now I'm writing tau h for the time constant for the high time when the output is high. And that time constant, of course, is the two resistors in series times the capacitor, Ra plus Rb times C. So again, to find the value of A, we evaluate the capacitor voltage at initial condition. So at initial condition, we know that the voltage across capacitor was VCC by 3, right, at t is equal to 0 positive. So we go ahead and then we put in this equation, and I'm not showing you the derivation, but basically that's going to be VCC by 3 is equal to VCC plus A using this equation right here when you put t is equal to 0, and then you can find A is equal to VCC by 3 minus VCC, which will be negative 2 VCC by 3. And that's what you see over here. The value of A is negative 2 VCC by 3. E to the power negative T over tau H. So this is when the output is high and the capacitor is charging from VCC by 3 and going towards VCC. Okay. So now what's going to happen? As it is charging and as it is going towards VCC, you can see the dotted line going towards VCC, which is a steady state. As soon as it will hit 2 VCC by 3 and becomes a little bit larger than that, what's going to happen? Let's go back to this. What's going to happen? Pin number 2 will be above VCC by 3 and pin number 6 will be above 2 VCC by 3 because they're tied together, right? So basically the voltage across capacitor just become greater than 2 VCC by 3 when it is charging, right? So this condition becomes satisfied and also this condition becomes satisfied because again VCC by 2 VCC by 3 is greater than VCC by 3. So as soon as this condition will be satisfied, the output is gonna go low and the discharge pin is gonna go grounded. So as soon as this condition will satisfy, right here, where is the waveform? Right here. As soon as this condition will satisfy, the output is gonna go low right here. Discharge pin is gonna be grounded. Now when discharge pin is gonna be grounded, when this pin is gonna be grounded right here, what's going to happen? This circuit is gonna become a source free circuit right here. C, RB and ground, and of course ground is here. So this circuit is gonna become what? Ground, C, RB and ground, right? So it's gonna become a source free or natural circuit right here, right? Now the voltage on the capacitor is at that time is at the start of this cycle is 2 VCC by 3. So this becomes a natural circuit, and for this natural circuit, whatever charge capacitor has accumulated, it starts dissipating that charge through resistor B. And we know that the natural circuit expression for the capacitor voltage is VCT is equal to the initial voltage times E negative T over tau, where tau of course now is tau L for the low time, because this time constant is different than the high time constant. This time constant is what? Capacitor C times RB, right? Capacitor C and RB. So initial voltage was 2 VCC by 3. So initial voltage e to the power negative T over tau L. Capacitor will start discharging according to this equation right here, according to this equation. And as soon, it is discharging towards 0, but as soon as it will hit 2 VCC, VCC by 3 becomes a little bit lower than VCC by 3, what is going to happen? Pin number 2 and pin number 6 voltage becomes less than VCC by 3, right? As soon as pin number 6 and pin number 2 voltage becomes less than VCC by 3, this is below VCC by 3, and of course less than VCC by 3 means that definitely of course it is less than 2 VCC by 3. So both pins, pin number 2 and pin 6, which are tied up together, their voltage are below VCC by 3. Condition A is satisfied, output will go back to high and discharge pin becomes open circuit, and the first condition is gonna be repeated again, that is capacitor will start charging now from VCC by 3 towards 2 VCC by 3, and in that course of course as we discussed, the time constant is going to be RB plus RA times C, and all that thing that we discussed is going to happen. So this is how this circuit is going to work, and this is how the timing of the capacitor and resistor circuit is used to create the output waveform, as we also discussed in the previous section of op-amp astable multivibrator. In that circuit, although of course our time constant was same when the capacitor was charging and discharging, so it was a square wave. In this case it's not a square wave, because the time constant is longer when it is charging and shorter when it is discharging. So basically, the duty cycle is basically how long the waveform is at highest state divided by the total time period. So the duty cycle is going to be greater than 50% in this case. So this is how the circuit is operating. Very simple operation, very simple circuit, used very commonly, of course. Now to figure out what exactly will be the value of the high time and value of the low time and the total time period, which is high time plus low time, we are going to use the two equations of the capacitor voltage when it is charging and discharging. So from equation 7.10, when capacitor is charging, we're going to use that when the capacitor will go to the time TH, which is the end of the cycle, high cycle, the voltage on capacitor is 2 VCC by 3. So we're gonna go ahead and plug in that value of capacitor voltage and then plug the value TH in terms of time and then solve this equation to get, after simplification, we're gonna get that the high time is natural log of 2 times the high time constant, which is RA plus RBC, and natural log of 2 is about 0.693. So this is the high time. And similarly, from the other equation 7.11, when the capacitor was discharging, we can figure out that the low time is 0.693 RB times C. So again, you can see that this is of course longer time because you also have another resistance. The resistance here is high, the resistance here is low. So of course TH is longer than TL. Total time period is going to be the addition of 2 TH plus TL, and the total time period is going to come out to be 0.693 RA plus 2 times RBC. Okay, so now the question is, of course, this is not a square waveform provider, or the oscillation at the output is not a square wave, it's a rectangular wave. So how to create a square wave? Now there are two ways that we can do that. One way is basically one way basically is to use the ideal diode. Now when you're using ideal diode, of course we consider that when the diode is on, there is no output voltage or there is no voltage drop across diode. Also, when the diode is on, the on resistance is 0. Now remember, ideal diodes, they do not exist in reality. In practical life, of course, there is usually voltage drop across diode when it is on, 0.7, 0.3 based on what type of diode you're using. And of course there is some on resistance as well, which is quite small though. In any case, if you want to have at least theoretically equal high time and low time, then what we can do is we can use an ideal diode in parallel with RB, right? In parallel with RB. Why? Because when you have the high output and when you have pin number 7 discharge open circuit, right? Then remember, if when diode was not here, then the current was flowing from VCC, RA, RB, and C, the first circuit that we discussed, right? So if the ideal diode is here, this diode is going to become open circuit as soon as the discharge is gonna go to open circuit. Remember, if the discharge is at ground, when the output is low, discharge is at ground, right? When it is ground, of course, then D1 is going to be reverse bias because the capacitor voltage here is going to be greater than the ground. So this D1 is going to be reverse bias. But when the discharge pin is going to go to open circuit, when the output goes high, then VCC of course is greater than ground, so this D1 is going to become forward bias and the current is going to flow through this route. Basically your RB is going to be shorted out by D1. So your time constant T high is going to be, in this case, right here, I don't have to rewrite it. That's going to be RA times C, because those are the only two components in the path of the flow of current. And when the output is low, Then pin 7 is of course grounded. When pin 7 is grounded, nothing is going to change, the capacitor and resistor and the ground and this ground. So that's going to be a natural circuit, source free circuit as we discussed, and this diode is going to be reverse biased because the voltage on the cathode of the diode is going to be less than the anode is grounded, and cathode voltage is going to be the voltage across C, which initially is going to be 2 VCC by 3. Okay, so the load time period is not going to change. That's going to be RB times C TL. So one time period is RA times C, which is the high time period. One time period is RB times C, which is a low time period. If we want it to be a square waveform, again, at least theoretically, because again we are considering diode to be ideal. So at least theoretically, if we want the waveform to be square, all we have to do is to take RA and RB to be equal, and the waveform at the output is going to become a square waveform. So that's one technique to do that. In practice, it's going to give you close to the square waveform, not 100% square again, but diode being not ideal, it's going to give you close to 50% duty cycle. That is, high and low will be close to each other, not exact. Now the second thing that we use is use another IC in conjunction with the 555 timer, and that IC is a binary counter. So you discuss different type of binary counters in digital systems. What binary counters do, basically they can count in binary. For example, if a 4-bit binary counter can go from 0 0 0 0 at the output to 1 1 1 1, they can count from 0 to 15 basically at the transition of the input cycle, input clock. So they can go in the first clock cycle, they can count 0 0 0 1, the second clock cycle 0 0 1 0 and 0 0 1 1 and all those things. So they can go as the clock cycles are going from 0 to 15, then the output goes from binary 0 to 15. Now the property of these type of counters is the output of these counters are the waveform of the output of these counters have 50% duty cycle always, right? So what we can do is we can use our 555 astable multivibrator circuit, use the output of that to run a counter. Now it can that counter can be 4-bit, it can be 8-bit. I'm just taking an example of 4-bit. It can be either 2-bit, right? And 2-bit you will only have the QA and QB. The most significant bit will be QB in that case, and the least significant is QA. This is the least significant bit right here, LSB, and this is the most significant bit. So if your counter is 4-bit, then you have QD, QC, QB, and QA, most significant to least significant. So you can use any counter, any binary counter. It can be 2-bit, it can be 4-bit, 8-bit, whatever. The idea over here is that if you want a square wave at the output between high and low, right? Then instead, and you want the 50% duty cycle, then instead of taking that from the output of 555 timer, use the output of timer to run a binary counter such that whatever frequency you want, whatever time period you want from for your output waveform, you can set that time period for any of the output here, and then you can calculate what time period will be for the output of 555 timer, corresponding time period will be for the output of 555 timer. Now you don't really need a square wave to run the clock, because clock activates once per cycle anytime, and it activates basically either at negative going transition of the cycle. So for example, if your 555 timer output is this, which is not a square, so it will either activate at the positive going transition of the clock once per cycle, or negative going transition of the clock again once per cycle, right? And whenever it will activate QA. So it will make the output transition of QA from either 0 to 1 or 1 to 0. So whenever it is activated, it's going to make the transition of your output QA. Now QA is used as the clock for QB, QB is used as the clock for QC, and QC is used as the clock of QD. So let me go and show you this right here. So this clock, although this clock is 50% duty cycle, but when you are using from your 5/5 timer, you don't have to have it 50% duty cycle. All you need is your high signal, and then your low signal can be anywhere, and then again your high signal, and then your low signal after 50% duty cycle, and then high signal, something like that. So this is the output of your 5/5 timer, which is acting as a clock now, right? And as you can see, the output of Q naught, they're showing Q naught, we're doing QA because these are from different websites that I copied. The output of Q naught is changing when the clock is going at the positive going transition of the clock. So positive going transition. So negative does not really matter, right? Irrespective when it is coming. Next time when it will be positive, which will be one complete time period, right here, right? Then this output is going to change again, right here. Right here, see, this output is changing again when the next positive is coming. So next positive is going to come, and this output is going to go back to 1. And Q1 is derived from Q naught. Again, if you look at this internal, there are 4 flip-flops in the timer. If you look at this, Q is the clock of QB, the QA is the clock of QB, and QB is the clock of QC, and QC is the clock of QD. The only 5/5 output is going into the clock of QA only, or Q naught in this case. So now what's going to happen, let's say, and observe that the time period in each case is doubling up. So this time period, so let's say this time period is T, or this time period is T rather, then this time period is going to be 2T, this time period is going to be 4T, not 3, 4T, this time period is going to be 8T, and this time period is going to be 16 times T. Okay. So let's say you want the time period, you know, of 10 millisecond, right? So you can set any of these at 10 millisecond. Let's say you can say that I want to set this at 10 millisecond, right? And then from that you can figure out what will be the time period of this, which will be 1/4 of T. 1/4 of this time period, this is TB, right? This is TA, TB, TC, and TD, right? So if TB is 10 millisecond, then T of 5/5 is going to be 1/4 of 10 millisecond, which will be 2.5 millisecond. So you have to design the timer for 2.5 millisecond, and that you can do easily by choosing different values of RA, RB, and C. Some value will be given to you, or you can choose some value, and rest of the values you can define such that the time period is going to be 2.5 millisecond, irrespective of what duty cycle you're using, right? That does not matter in this case. So this is how you know, you can get a square wave from a binary counter, the clock of which is derived from 5/5 timer. So I think I have one example over here based on this, or 2 examples rather. This is from the book, in which you are consider the 5/5 timer. You're just calculating the high state time, low state time, period, and frequency and duty cycle. So you know, the equations are pretty straightforward. Values are given, so you're just putting the values and calculating the required results. And this is not in the book, this is I'm giving you based on what I just explained about the binary counter. So 5/5 is stable, a stable multivibrator providing clock frequency to a 4-bit counter, the frequency of the least significant bit, that is A, the top one, of the binary counter is 16 kHz. Calculate the value of RA and RB if the duty cycle is 70% and capacitor is 10 nanofarad. So remember, the time period of A is double the amount of time period of the 555 timer. That means the frequency of A is half of the frequency of 555 timer. So when the frequency of A is 16 kilohertz, frequency of 555 timer will be 32 kilohertz. The corresponding time period will be 31.25 microsecond. 70% is the duty cycle. That means high time will be 70% time 31.25 and low time will be 30% time 31.25. And then we can use the low time equation and high time equation. Since we already know C, from the low time equation we can figure out what is the value of RB, and from the high time equation now we know RB and C, so we can figure out what is the value of A. So this is the last example of this chapter.